Good morning. It's great to see a good turnout today. We'll just start slowly, as I think there's a few more people just joining as we begin. Firstly, I'd just like to introduce myself. I'm Sharee McNab, a research engineer at the EPECentre, and with me is my colleague Josh Schipper. I don't know, our screen was on. And he's a research engineer at the EPECentre as well. And today we'll just be sharing with you some work we've undertaken on an EV hosting capability project. So we're looking at the effect of EV charging in LV networks. I'm going to start the presentation, and Josh will step in halfway and present the second half. So this is a follow-up to a workshop we held back in April in the dark days of lockdown, when we were soliciting some feedback from EDBs around modelling. And so it's good to see a number of those people here today. And this is just to show you what we've come up with. So the workshop objective is to describe the modelling approach that we've developed. It's focused on the effect of increasing levels of EV charging, and that's really focused on the residential parts of the network. I think we all know why we're interested in this, and the figure on the right captures that. It's data from the Ministry of Transport EV fleet data. And in the past 5 years, we've increased from pretty much 0 EVs to over 20,000. So that's a big increase in EVs, and that's going to have a big impact on what's happening in the residential parts of our network, which is where the majority of charging takes place. Now I'm going to focus in mainly on the purely electric vehicles, so looking at both the new and used electric vehicles. And that's because it removes any ambiguity around the interplay between the electric engine and the combustion engine. They're also the largest majority share of EVs, and they're also expected to have the biggest impact on our LV networks. The plug-ins have typically smaller batteries and less impact. So we'll discuss the assumptions we've made, and we'll illustrate the type of results that can be obtained by going through a case study example. Just before I continue, you're welcome to put any questions in the chat. We'll probably leave questions till the end, and people can also speak their questions too. So just to give a brief outline of the talk, we'll start by looking at the modelling approach that we've taken, a high-level view of the architecture, the main processes in this architecture being the scenario builder and the power flow solver. And then we'll look at the results part by use of a case study and have questions at the end. And as I said, you can either put these on the chat or ask them at the end. So the modelling approach we've used is really looked at deterministic versus probabilistic. Using a deterministic approach would give us a single EV hosting capability for a single set of conditions. So that really relies strongly on choosing the right inputs for the simulation. In this case, we feel there are a range of inputs and a range of uncertainties. When we previously did work for DG Host looking at PV hosting, in some ways this was a much simpler problem, and we could look at the worst case by considering what was happening, say, at the midday of when the sun is at its strongest and typically loads are at its lowest. So you could get a reasonable PV hosting capacity using those scenarios. It did have a probabilistic element in that we looked at different placements of where the PV might be in the network. The EV scenario ends up being a lot more complicated. We have a lot more inputs that can affect our results. We have people who are less well behaved than the sun. They go out and drive their cars at different times. They want to charge at different times. And there are a whole range of different EV models and different capacities and charges being used in the network. So the trade-off for using a probabilistic approach, however, is that you have a large computational requirement because you're exploring a wide parameter space. And Josh will talk a little bit more about what we've done to solve that issue. The results are a distribution of values, so it's a more complex result space because you're looking at a whole lot of probabilities of what could happen in the network. So the probabilistic approach is what we're taking, which is involving using a large number of scenarios to explore. So the model architecture, if we look, there's 3 main process bubbles in yellow. On the left, we have the scenario builder that creates the different scenarios to be looked at. This calculates load profiles, which then gets passed to the power flow solver. This is the real engine, which takes into account the network that we're solving for, looking at specific load profiles and looking at the network violation criteria. This gives outputs of the power flow outputs, which pass to a results processing, which tries to put these results in a way that's meaningful and useful to use. So what I'm going to concentrate on firstly is the scenario builder on the left and the different inputs, the different distributions which feed into this. So looking at the scenario builder, this has 2 main roles. The first is to define the scenario at each ICP. Initially, a base household load is assigned to the ICP, and then it's decided whether an EV is present at the ICP or not. And this will vary depending on where you are in the penetration, like how far through the penetration selection you are. So if you've got a low penetration, there's a low likelihood that you'll have an EV at the ICP, whereas going up to the 100%, always have an ICP with an EV present. I like to think of the scenario builder as selecting inputs as using a number spin of a wheel. So for looking at the interesting case where an EV is present, you spin the wheel and look at what battery capacity you come up with. Now, this battery capacity encompasses a number of models behind it. And for each battery capacity, we have a separate distribution to define the likelihood of what charger rating it might be happen. So in this figure here, we've spun the wheel, we've selected a 24 kilowatt hour battery, and the charger rating has ended up being a 3.6 kilowatt. And you can see the relative likelihoods by the area on the circle. The next spin the wheel is you spin it and see what is the behaviour of the EV user going to be like? How do they want to charge? So out of given 3 options, in this case, a charge before morning is selected, and we'll talk a bit more about those later on in the talk. Now, the next final spin of the wheel is what is the EV use going to look like? And it selects from a journey database a particular index into what trips are going to be taken over the course of a week for that ICP. So this is done time after time after time for each ICP for thousands of scenarios to give a distribution of results. The next step of the scenario builder is once we have these parameters for what the situation looks like at the ICP, what does that do to our EV load? How does that translate to when the EV is charging? So the output from the scenario builder is an EV load, which says the load at each time period over the course of a week. And there'll be more about that later. So now I'd just like to look at the different inputs that go into the scenario builder. The base household load, and this is prior to the EV load being incorporated. We have smart meter data with access to over 20,000 ICPs worth of data over the course of a year. It's in half-hourly demand, half-hourly data level. And what we do is we look at the highest demand week in summer, maybe in winter and maybe summer, to try and get the worst case week to be of interest. The next distribution that we're looking at is the battery capacity. And to create a distribution around the battery, we looked at the number of EVs in the network and what make and model. We made use of Ministry of Transport data from up to the end of June, and this gave us over 15,000 EVs. So we looked at the top 96% of the electric vehicles, which incorporated 17 different models, and we looked at what capacity those models had. Some of these are a little bit more complicated. They have multiple battery capacities. As a model has progressed, we have seen manufacturers introduce larger battery capacities. We've also seen options such as Tesla offer different battery sizes with a software switch to either limit the battery capacity. So we use this information, the model, the date of manufacture, also the country of origin, which can affect the capacity, to create a battery distribution for the capacity. We then bin the EVs into 8 capacities. That's just to make it more manageable. So obviously we have to have some rounding because we've got discrete capacities that we look at. And one additional consideration that we have looked at, and this is just the Nissan Leaf, we consider battery degradation. And that's because the Nissan Leaf's more noticeable in that it seems to have more battery degradation. It doesn't have the thermal management that majority of other models do, and they also are the highest model in the New Zealand fleet. So we apply a battery degradation of about 3% per year, and so we were able to create a table and bin those different models into those capacities. And if you look at the pie on the right, you can see that the largest distribution is of the 20 kilowatt hour battery capacity, and that's made up largely of the second-hand Nissan Leafs. Obviously, these distributions can be changed very easily as required. So once we have a capacity, we then need to determine what charger rating is going to be used. And as I said earlier, this can vary depending on the model. So we've looked at what component of the models make up each of these capacities and produced a likely distribution for each of those capacities. We've used the onboard charger rating for the model to guide us to what level of charging is possible. And in general, the lower charging rates are common residentially at the moment, Tesla being an exception as they provide their own charger with each vehicle they sell. It's very difficult to get an absolute gold standard view on the charger rating, but we were also lucky to be receive some assistance from Orion, who has conducted some user surveys as well to inform these choices. So when we look at how the EV is used, we created a database of journeys, and this was taken from journey data from the Ministry of Transport surveys. These are published 2014 to 2016. They have a wealth of information about the trips taken, where they originate from and to, the times, and for a number of cars in a household. However, this did require a significant amount of post-processing. It's great that it was a large data source. We've used over 2,400 households, and it's great that it's New Zealand based, as it makes it relevant to our networks. However, it's largely ICE vehicles rather than electric, so this may have some impact, but I think only limited. The other issue with this data is there was high rates of recorded errors, for example, cars leaving before they'd arrived. Because it was so detailed, it actually left quite a lot of room for error, so that was quite challenging. But what we've done is taken these households, we've simplified the data into only allowing for 2 trips a day, and that was because we've looked at information from studies such as My Electric Avenue, and you see that there's a lot of days where cars are not charged at all, or maybe they're charged once, and some are charged twice. More than this is quite rare. So I've simplified this to a single household, single car at a household, a maximum of 2 trips. We've looked for the largest gap between their various journeys and created this database. On the right shows a bar graph which shows the typical distances travelled in this database, and you can see that the 50 to 100 is the most common distance travelled in a week. If we look a bit deeper into the journey database, if we look at the distribution of arrival times, this is great. We have a real source of data. You can see that I've plotted the time along the x-axis and the number of arrivals on the y-axis, and we've looked at a weekday in blue and in red a weekend day. You can see for the weekday, the most common time period to arrive home is about between 5 and 5:30. But this is quite useful because it provides greater diversity than previous studies have allowed. So another parameter that's used in our scenarios is charging behaviour, and this one can be quite useful if we want to investigate the impact of encouraging different charging behaviours. On the right, I have a timeline just for an example day. We have a vehicle that happens to have arrived at 7:30 at night. It's scheduled to be departing the next morning at 7:30, and we look at what the different charging behaviour, how it impacts when the charger is used for charging the EV. The first case is charge on arrival. This is essentially the user gets home in the EV, they plug in and charge straight away. It happens to get fully charged up just before 3 AM. The second case is if a householder has time of use tariff and might choose to charge at a cheaper time to take advantage of the lower electricity rate. This example, the time of use gets cheaper at 9 o'clock at night, so they program it in to start charging then. And the third type of charging is charge before morning. So the car is programmed to say that it's leaving at 7:30 the next morning, and the charger is set to make sure it charges before it departs. So you can see that's the impact of the different charging behaviour depending how the EV user has been assigned. There's a secondary factor we applied to our EV users, and that's referred to an anxiety factor. For those of you who have been to Ewan McGill's talks, he talks about this too. So we assign a factor between 0 and 1. It's given a normal distribution with a mean at about 0.75. And what this means is at 0, the EV user is pretty relaxed. It doesn't mean to charge until it really has to. Whereas if you're an anxiety factor of 1, the high level, you're pretty nervous. Every opportunity to charge you will take. So you'll notice that the distribution extends past 1. All those users past 1 just get assigned an anxiety factor of 1. Now this factor gets used to define when the user will charge. So if we look at the state of charge of the battery and it's below this threshold, charging will be conducted. Otherwise, it might be left to after the next trip. So lastly, once the scenario has been set up, the next thing to do is to calculate the EV load profiles. The scenario builder does this by initially starting with a randomly assigned state of charge for the battery, and then the state of charge gets monitored and updated for each trip and each charging event. The most complex decision is actually when to do the charge, and this is dependent on the charger behaviour, the anxiety factor. It will also look ahead to the next trip, taking into account that if there's a large trip planned, the user is likely to want to charge even if it's still got quite a lot of charge left. And it makes a decision based on the time available for charging too. So some of those charger behaviours get overridden if there's only a small amount of time to charge to the next trip. So that gives you an insight into the scenario builder. That feeds the load profiles through to the power flow solver, and I'm going to let Josh take over from here.
Thank you, Sharee. So I'm going to take the inputs that Sharee has developed, both the household-based demand and the EV charging profiles, and solve power flows on the LV networks of interest. For us to perform these power flows, we require some information about LV networks. Most of this information is provided by the client in the network database. However, some information isn't readily available, so we will make appropriate assumptions where required. In this diagram, we'll also have a box for network violation criteria. These are constraints to identify operating conditions on an LV network that are being exceeded. The network database consists of 5 tables. The first table is the network topology table, where each row represents a branch in a subnetwork. It is helpful here to introduce the term subnetwork. Sharee did mention it earlier, but we'll define it a little more. When power flows are computed, they are done so individually for each subnetwork. That is for an LV transformer and all branches connected to the secondary side of that transformer, as shown by the example here on the right. Although these tables can list multiple subnetworks, they are not solved together in one large network model. Network topology is then determined by the pairing for each branch. Network topology is determined by the node pairing for each branch. Then ICPs can be attached to each branch. And if there is more than one ICP, then these can be evenly spaced along the length of that branch. The network topology table also includes information about the length of the branch, the conductor type, and the number of phases that branch has. These columns are not shown on this table. The second table, the transformer table, and the conductor table provides impedance information for the subnetwork. A fourth table, the node table, is used in cases where the ICP connections are well defined. Finally, the ICP table contains the number of phases each ICP is connected to and the type of loads each ICP is. Not all information that is required is readily available. Therefore, assumptions are made for these parameters. Firstly, for the nominal voltage on the primary side of the transformer is known. However, the actual voltage has to be assumed. Secondly, the stiffness of the network above the LV transformer is assumed by a short circuit power. An earthing resistance is placed between neutral and earth at each ICP connection with an assumed value. Lastly, there is an option for load balancing. Moving on to the network violation criteria, the transformer highlighted in this figure is given an apparent power limit to analyze overloading. Each node, viewed as a horizontal bar, are given steady state voltage limits. These are typically the plus or minus 6% limits. Lastly, each branch, marked here by the orange vertical line in the diagram, are given a limit determined by the conductor type. Now that we've obtained all the information required to perform a power flow, we can define penetration level and scenario. This will show that we are doing a probabilistic modeling that Sharee mentioned at the start of this presentation. The diagram represents a subnetwork, each dot being an ICP. Some of the ICPs have electric vehicles, while others don't. The ratio of the total number of ICPs with EVs and the total number of ICPs is the penetration level. For this analysis, we set the penetration levels. For each penetration level, we solve thousands of scenarios. The result is a distribution of the values for each variable in the subnetwork. Therefore, this is why we consider the analysis to be probabilistic, because the results are distributions of variables that give the likelihood of a condition to occur. Each scenario is run over a week. That is, for each 30 minutes in a week, a power flow is solved. This allows for EV state of charge to be analyzed over a period longer than a day, covering both weekends and weekdays, but not extending computationally the burden of solving for this long. The week chosen in the year is also to reflect the peak electricity demand. The scenario is built by randomly assigning electric vehicles to ICPs according to the penetration level, and then assigning electrical loads in the manner mentioned by Sharee to the ICPs and the EDBs. The number of power flows to solve presents a challenge. For one subnetwork with 100 ICPs, with 8 penetration levels and 2,000 scenarios per penetration level, and 336 trading periods per scenario, the total number of power flows is high at 5.4 million. My desktop computer can solve 100 power flows per second, which requires about 15 hours to solve. A time that is considered too slow, especially if a client would like to analyze quite a few subnetworks. Therefore, we have developed an approximation method to speed up the solving process, which we'll go through now. Before we get into detail about the approximation method, it is important to understand that the figure on the slide fits in with what we want from a power flow. Solving a power flow is to solve a set of nonlinear algebraic equations, usually given a set of real and reactive power injections into each node of the subnetwork. The output is a set of voltages for each node. Then from these values, we can determine the currents in the branches and the power supplied by the transformer. If we adjust the injected powers and solve the power flow again and continue to do this, we trace out a relationship between the injected powers and the outputs we require. Therefore, we can get a curve that looks like the one shown in the slide, between one input and one output. In all practicality, we will never solve enough power flows to produce this curve, especially because if we have a system with 100 ICPs, we will have at least 100 power inputs and 100 voltage outputs. But for the purposes of this illustration, we will assume such a curve exists and all other power injections in the subnetwork remain constant so that we can look at one plot with one input. The approximation is formed by calculating the first order Taylor series expansion around an initial point. For this initial point, a power flow is solved directly. The first derivative terms of this Taylor series expansion, which gives the slope of the approximation, are solved from a linear set of equations derived from the power flow equations. Therefore, when we calculate the voltage for an injected power, like we have at point S1, we evaluate the approximation at that injected power to give our solution. With any approximation method, we introduce an error, and we want to try and reduce this error, and we've developed two methods of doing this. The first method in reducing error is to create multiple approximations from several different initial points. There are roughly 50 to 100 of these for any subnetwork, but this all requires one additional step. to find the closest initial point for each power flow. From this slide, it is the initial point with the shortest distance between the x-axis and from the point S1 in which we want to solve the power flow for. The second method occurs when, after applying the linear approximation, the result is in close proximity to the voltage limit, that is within the limit proximity region. Therefore, the Taylor series expansion is extended to include a second order term as well, forming a quadratic approximation. It's not desirable to apply the quadratic approximation continuously. That is not just to solve every node of voltage, branch current, and transformer loading for every scenario, because the time it takes to apply the quadratic approximation is an order of magnitude longer than applying the linear approximation. However, applying the quadratic approximation when we are close to the limit provides greater confidence in the results when it matters. That is, when we're trying to assess the risk of violating the limits. Applying this approximation method to our 100 ICP hypothetical subnetwork, we have improved the solve time by a factor of 20, so that instead of it now taking 15 hours to execute, it now requires only 45 minutes. This is a substantially better solve time. Moving to the results, by taking the outputs from the power flow solver, we produce a report summary and a results database. Results from the database are also plotted in a series of line graphs showing the trends as the penetration level increases. Results of the rest of this presentation show these plots for a case study. After solving all the power flows, we have distributions of voltages and currents for each node and branch in the subnetwork, and a distribution for the transformer loading as well. To record each distribution, we retain a series of percentiles, and to retain any more information would be too much to report or to humanly consider. Therefore, this figure that we show in the slide is presented as a legend to the other plots that will come later after it. The percentiles are shown by the letter P and then its percentile value. These percentiles are given the interpretation of the expected number of half-hour periods in a week that a voltage, current, or transformer loading will be above or below a given value. For example, top 2 HH, which means half hour, means we expect at least 2 half hours for the variable of interest to be above a given value in the analysis week. Although these 2 half hours do not necessarily have to be consecutive in time. For the top 0.1 half hour, the interpretation requires further clarification, as we are only dealing with time resolutions of 1 half hour. Therefore, we interpret this value as a 1 in 10 chance of a half hour in a week exceeding the given value. For the case study, we analyze a 50 ICP subnetwork with all branches having 3 phases and all of them being cables buried underground. We have also highlighted some of these branches, as these will be useful in some of the later results. The first result is the distribution of transformer loading, or rather its utilization. Here the percentiles are shown as lines, and as penetration level increases, we can see that some of these lines also increase as well. The most noticeable feature of this plot is that the median barely moves, but the top 0.1 half hour increases substantially, therefore implying that the EVs widen the range of loadings on the transformer. Also for the subnetwork, the maximum limit is never reached. The second plot is the distribution of all node voltage within a subnetwork, and to compare the overall distribution with that of the worst case node. That is seen by the line named high stress branch, bottom 0.1 half hour. Also, we can see from this plot that the minimum line clearly lacks any trend. Therefore, it's not recommended to form any policy based off this line, as it is heavily dependent on exceptional scenarios that may not arise across all penetration levels. But it's also good to mention that since we're doing 30-minute power flow solves, that we could expect within that 30 minutes exceptionally low voltages. This doesn't mean that the minimum line isn't useful. It just shows you the wider range of exceptional scenarios. The next plot again considers voltage distributions, but focuses on the worst case branches, which are branches 9 and 25, those that are at the end of each feeder. Normally we provide 3 such plots, but to show these plots on the slide, we have limited to 2. Worst case branches are determined by having the lowest average bottom 0.1 half hour percentile across the penetration levels. For the 4th plot, we show the worst case branches, or the worst case branch currents. To compare different conductor types with different maximum current ratings, we show the results in per unit values. It is noticed that the most stressed branches are the ones closest to the transformer. This is to be expected for situations where we have the same conductor type being used throughout the subnetwork. We provide 2 figures for worst case branch currents, one for this slide and one for the slide to come. This one plots the results by penetration level. But for the 5th and final plot, we want to show changes in branch current by the number of downstream electric vehicles from that branch. This is because we know branch currents are more dependent on loads below that than what is occurring on other feeders. Therefore, providing this information, we can be more precise on when issues may arise for a feeder. This brings us to the end of the results and to the end of the presentation. We have now presented a tool to assess impacts of electric vehicles on low voltage distribution networks. Thank you for coming to listen, and we'll open up the Zoom chat for some questions.